שכתבו שם בלוקים שהיו של קודם.
כן, אבל לא יודע, מטלב הוא טוב לדברים מאוד מסוימים.
לא, אני לא מגיע כשאתה
כן, זה... ביי, תודה. כן. אני עניתי, רגע, מה קוראים לך? אני עניתי לך. לא עניתי לך? תבדקי עוד פעם, כי אתמול שלחת לי ביום שלישי, שלחת לי בראשון אחד ובשני אחד, נכון? אתמול אחד ושלשום אחד. ועניתי לך אתמול אחד, תבדקי. אם לא קיבלת, אז תגידי לי, בסדר? Okay, so hi everyone. So today we are going to talk about the ROC curve, multiple observations, and then a little about Markov chain. So let's start. By the way, are there any questions about the exercise? Something important?
How do you get rid of the accent in the French text?
What do you mean?
Kind of sign, like an E with a...
Oh, yeah. So it depends if you are in MATLAB or in Python. MATLAB. So I think it will do it automatically. Just use the default text reader. It's supposed to do it automatically. For everyone, it's fine. Yeah, I think for most of the time it should be fine, but if not, let me know and I will help you. Can ask.
So I guess we can just throw the sample away.
What?
Like I can just pick randomly from the French text, and if I get something with an accent, so I can just.
It's also a possibility. Okay, more questions? Yeah. Okay, so this week there is no exercise. Yeah. Just let it go. Okay, so let's start with the ROC curve and the Neyman-Pearson lemma. So let's suppose that we have a threshold test, lambda theta, okay, and we accept age of 0 if the likelihood is bigger than some theta, right? P of x given W0 divided by P of x given W1 is bigger than theta. Okay? And we have alpha and beta, the two errors. So the Neyman-Pearson lemma just tells us that for each other test, that it can be a ratio test, or it can be some other test that you want, any other test that you want, if alpha of lambda. Okay, so we choose some other test. We call it lambda. If alpha of lambda is smaller than alpha of theta, this alpha is the alpha that we get from the ratio test, the likelihood ratio test. Then beta of lambda is at least beta of theta. Okay? And if we have here, if alpha of lambda is smaller than alpha of theta, we will get what? Here it's strictly smaller. Then we will get that beta of lambda is bigger than beta of theta. Okay? So basically it says that a ratio test is the best that we can do. If we want to play with both alpha and beta.
So that means decrease one error will increase the other one, right?
Yeah, exactly. That you cannot decrease alpha without paying something in beta. Okay? And it's important to know that the other direction is not true. Okay? So for some general test, the condition that beta of lambda is bigger than beta of lambda theta doesn't tell us anything about the alpha. Okay? So if we have beta of lambda, okay, if we know that beta of lambda is bigger than beta of lambda theta, okay, this is not true that alpha of lambda is smaller than alpha of lambda theta. This is not true.
And why is there distinction? It seems to me that you're just moving the ROC curve and
No, there is symmetry. The ROC curve is 1 minus beta. Is 1 minus beta. There is no, because here we say something different. We say that if we know that this is bigger, right, it doesn't tell us that this is smaller, because it can be any test. You don't know anything about this test. It can be optimal, it can be not optimal. So if we get a bigger beta here, maybe we get a bigger alpha also here, but we don't know it.
but it is correct if beta of delta is smaller than beta of theta, then alpha of delta.
Yeah, exactly. Okay?
For this direction is correct, but this is wrong.
Yeah, exactly. Right. It's not if and only if, it's just one direction. Okay?
Are you going to prove it or?
No, Tali proved something similar, right? The Walsh lemma in the lecture. I will not going to prove it. If you want, I can, but I don't think it will give you something. But it's not. Maybe I will do it next week if you want. But it's not difficult to prove it. Okay, so let's questions. More questions? No. Okay. So as I said, it's a very important lemma because it tells us something about the optimality, the best test that we can do. So Now let's suppose that we have two random variables, x given w0, that is distributed as normal distribution with 0 mean and variance 1, and another random variable that x given w1 is distributed as random variable with mean 1 and variance 0. And we saw this mean 1 and variance 1, mean 0 and variance 0. Okay? We saw
This is right?
this is right. Yeah. What I say?
No, because what you said was inconsistent.
No, this is right. Sorry. Sorry. Okay, so we saw last week, right, that the threshold test, that the decision boundary of this is x smaller than log of 1 over theta plus half, right? And everyone remember this? No? Okay. Okay, and now we want to find some test that the test, let's call it lambda, that alpha of lambda is smaller or not bigger than some alpha prime. Okay, we have some constraint on alpha, and beta of lambda is minimal. Okay, so now we have these two distributions, and we want to find some test that will give us some constraint on alpha. We have some constraint on alpha, and we also want that beta will be minimal. Okay, the best test that will give us this constraint. So what we need to do, what the lemma, the name and person lemma tells us?
You should take alpha to the alpha prime and then beta to the...
Right, that we only need to consider some only the likelihood ratio test, first of all, right? We need only to consider the likelihood ratio test because this is the optimal thing that we need to do. Okay, and it also tells us that we need to find a threshold test that this will be that this inequality will that alpha lambda will be equal to alpha prime. Okay, because we need the best thing that we can do is to achieve our constraint, and only then to find the minimal beta. So so we just need to, we have alpha, right? Alpha prime. This is equal to, we want that it will be equal to our alpha lambda theta, let's call it. This is our test that we want to find. And we know, right, we saw last week that the likelihood ratio test, in this case, the decision boundary of the likelihood ratio test is the integral between some t, let's call it t of theta. Okay, this is t of theta. Questions?
The theta in the name and field lemma, is it delta theta or the...
You can write here delta theta. It doesn't matter if you want, but it's the test. It's the likelihood ratio test with some theta. Okay. So we saw last week that in this case we have integral between t to, this is alpha is equal to the integral between t to infinity f of x given w0 dx. And what is this for a Gaussian distribution? One minus? Yeah, right. So this is it exactly. So we have this solution. Okay. What? This is the CDF of the standard normal distribution. Okay, and we have here a Gaussian with a mean 0 and the standard deviation and variance 1. This is exactly the CDF of. This is 1 minus the CDF of the standard normal distribution. Okay, and we can find t as a function of alpha prime. From this, we can get that t is equal to phi minus 1 minus alpha prime. Okay? So we find t, we need the decision boundary. T is our decision boundary, will satisfy this chance. Okay? And in many cases, we don't really need to say what is the actual threshold theta. Okay? So we only care about the decision boundary. We only care about t. So we have two distributions, and we only care about what is decision boundary if we see some example that is equal to this, or example that equal to this, and we don't care about theta. Okay? So here, for example, we don't know, we didn't get explicitly theta, but only implicitly. Questions? No. Great. So now, okay. So now let's see what is in the same case. What is all the possible values, all the possible pairs that we can get for alpha and beta? Now we don't have a constraint about alpha like we had before. Now we want to find all the possible values, all the possible thresholds, all the possible decision boundaries that we can get. And we want the optimal alpha and the optimal beta. So how can we find it? We have alpha, right? We have alpha. We have alpha as a function of the decision boundary. And now we want to find beta. Okay? So what is beta in our case? Do you remember from last week? Right. The integral from minus infinity to t f of x given w1 dx, and this is equal to the CDF of the standard normal distribution, but because of this is not standard normal distribution, right? We have mean 1, so we need to take phi of t minus 1. Okay? And now the set of all possible values that we can get is the set of alpha and beta. T minus 1 when t can be any value in the real numbers. Okay? So here we define the set of all the possible alphas and beta that will give us the best test that we can get, the best errors that we can get. So and now, of course, what? Here?
E belongs to R.
Ah, it's T. Sorry, T. T belongs to. Okay. And now, of course, that we can find beta as function. If we want, we can find beta as function of alpha. We just need to substitute, and we get beta is equal to phi of phi minus 1, y minus alpha minus 1. Okay. Now, in many cases, we are interested in alpha. This is the false positive, right? And we are also interested in the y minus 1 minus beta, that this is the true positive. Okay, so we are interested in these two terms, the false positive and the true positive. So this is exactly the RC curve. Okay, Tally talked to you about the RC curve. Okay, so the ROC curve is exactly the set of all the possible alphas that we can get and y1 minus beta. In the positive real numbers. Okay? So this is the definition of the ROC curve.
It's defined for a test,
For a specific threshold. It's not a test. Yeah. There are many tests that can achieve the same threshold. The ratio test, we know that it achieved this threshold. Okay, so let's see some properties of.
You have to define what your threshold, right?
What?
You have to define what your threshold is before.
So let's see. Let's see for example how it looks like. So we have. Okay, so let's suppose that we have two distributions. Okay, let's suppose that they are Gaussian, something like that, and and now we have some threshold. Okay, let's suppose that it's here, for example. Here. Okay, now what is. So of course that we know that this. So this area. What is this area?
Which distribution is the one to the right?
It's general figure.
Yeah,
it's not.
W0.
Okay.
It's
Yeah. So
W0.
this is W0. Yeah. This is W0. This is W0. Okay. So this area. What is this? It's the true. It's It's not a rejection. It's the heat. It's the correct acceptance, right? We accept. It's.
Depends what you reject.
Oh yeah, it depends. But you understand. So in this area we will accept W0 and it will be correct, right?
That's when you took theta to be 1, right? Because the threshold is 1.
No, it's a general threshold. I didn't say anything about 1 or something like that. General.
Said something about the what's bigger, the p x omega 0 or p x omega 1.
I didn't say anything about the probabilities. Just I plot them on the board. It can be anything. Like let's suppose that there are two. Let's suppose there are two Gaussian, and of course the mean of this is bigger than the mean of this. This is all you know. And now let's take a general threshold. Okay, this one.
But shouldn't the acceptance area be everything on the right of the threshold under W?
Yeah, sure, the acceptance area, of course, no. So, right. The acceptance area is all this. Okay? This area we will accept, and this is we will reject. Now we want to check what are the cases that we are correct, right? So when we are our decision will be correct, right? In this case.
I have a question because you just marked the parts of px omega 0 which is larger than px omega 1, right?
Yeah.
Area. So it means that theta is equal to 1.
No. When theta will equal 1, the decision boundary will be in the intersection. Only in this case. This is only when in what cases we will be in our decision will be correct. Only in this case, right? Because if, for example, if we will see sample in this area, so we will say that it's W0, but the true thing is that it will come from W1. So it will be a false. Yeah.
But the hit area also includes the area, like everything right of the intersection. It's also the area underneath the W1.
Here. Well, here. Yeah. What? No, here.
Right of the intersection.
All this area.
Yeah, everything right of the intersection would be the correct acceptance of H1, H0, right?
No, yeah, but it will not be.
I'm not sure.
It will be so it will not be correct.
But after right of the intersection.
Ah, yeah, right intersection. Yes, yeah,
Because
yeah, everything.
Oh,
okay.
Area,
yeah, okay. So everything under the area right of the intersection. You're right. So everything. This is the intersections, and so every example that we will see right in the intersection.
But you will also, it will also be hit if you take the area that I can see now, like there, like
Here?
under H0, but to the right, the point you didn't mark and there. This will be also correct.
Yeah, everything. Yeah, everything. Yeah, just let me finish. Okay.
That will be not correct because
No, that will be correct.
higher.
No, that will be. Just a second. Okay, just a second. Everything that we will. Let's do it. Okay. Everything in general. This is our decision boundary, and we will choose the W0 if we will see samples when we are in the right area. Okay. Everything that comes from the right area of our decision boundary. Okay. This is understood. Great. Now, when our decision will be correct, okay, when it will came from the right distribution, from W0, okay, so it will came from the right distribution only in this area, okay, only when.
No, but it's really how you define the error, right? Because it could even really to the left, it could have if there is some small probability it could have come from W0.
Yeah.
So Gaussian,
Yeah, of course. This is our problem, of course.
Yeah, so it depends on the error.
Depends on?
On the error. It depends what you want to, what error.
Yeah, sure, of course. But just a second. So we have two types of error, okay? We can get error that we will choose W0 and it will be W1. Okay, so it's this area. Okay, so it's this area. And we can choose W1, but it will actually be W0. Okay? So this is this area. This area. Okay?
In the area that you have the overlap, so you can either get this I mean, like where the overlap,
Yeah,
triangle.
this area, yeah.
Yeah. So you can have this arrow with certain probability and the other arrow with
Yeah.
certain probability. It's not zero and
No, it's not 0 or not, of course.
But everywhere it's not zero, like I saw in the
no, but there is for sure correct.
No, because there is
No, it's a Gaussian, you're right. It's a Gaussian and it can, so you're right. You're right. It's a Gaussian, so it can go to infinity. Okay, so now let's see. So we have two distributions, and now let's see the more questions. Okay, so now let's see the ROC curve. So this is 1 minus beta, and this is alpha. And the ROC curve, so this is okay, so we have here some curve for all the possible values of alpha and beta and 1 minus beta, and then for each threshold, for each decision boundary, we have some point on this curve. So, for example, so first, if we choose this one, okay, we will have a higher alpha, but also 1 minus beta will be big. And if we choose this decision boundary, we will get smaller alpha, but also 1 minus beta will be smaller. So it will we will get this point.
Isn't the whole curve for a certain threshold?
No, for a certain for specific threshold, we have a point in this curve. The curve is for all the thresholds. Okay, all the best. For each threshold, we have the best point that we can achieve.
Sure.
Yeah.
If we go back to the Neyman and Friedman, it says that if you find such threshold, such that if you it's about the test.
Yeah. So the Neyman, okay. So the lemma just tells us that if you take a test with a ratio test, you will be on this curve.
But on this curve,
What?
but if you choose different,
Okay. Is it clear? Okay. So
so you can define a test by a curve.
what do you mean to define a test?
Like if you look at, I understand that each point on the curve is a certain threshold. If you have
Yeah.
a trade-off between.
Right.
But what defines the whole curve is the test that you use?
I don't think that I understand it, your question, but maybe there are many tests that can achieve the best single point in this curve, in the ROC curve. It can be, it doesn't have to be a ratio test, but for a certain alpha or a certain best test, a test that is optimal, okay, you can, for some test that is optimal, you can assign some theta. Or it's the same as say that you will assign it to a point in this curve. What?
Maybe I will.
Okay, so come to me later.
Can you show again graphically what is alpha and beta in the case of two Gaussians?
Yeah, sure. So
maybe with two different colors as we do here.
If what? Sorry?
With two different colors.
Yeah, maybe I'll reuse two different colors. So, okay. So, this is alpha, okay? And
Earlier we defined alpha as the integral from t to infinity.
GT, right, so this,
Oh,
yes,
so
right.
all
All this till here. Between t to infinity of this, okay?
omega 1.
This you said is false negative,
Right. False, false alarm.
False positive.
False positive, yeah.
But
False negative is the other direction. It's false alarms. When we say W0, but it's actually W1.
but it's not.
So I'm sorry if
You
you...
said everything
Yeah, it's
right of the
double.
intersection is not alpha.
Because it's infinity.
No. So maybe...
Correct, except
So yeah, maybe I didn't say it right. This is alpha. All the integral between our decision boundary to infinity of W1. So
Beta.
But
It's beta.
yeah, that's what I'm saying.
Alpha.
no, this is
No,
alpha.
but if W1 is H1,
No,
when W1 is
W0.
H0,
W0 is H0.
yeah, but
The-
W1 is H1,
Oh yeah.
so the area in H1 is beta, it's not alpha. Alpha is under H0.
You're right. So we have this is
Okay.
sorry. You're right.
What was that?
You're right. You're sorry.
So it will be false positive.
So it will be false positive. Yeah, it's
Which one is?
that. Sorry.
But
You're
in the
right.
other
I'm
case-
sorry.
In the other case, this is
This is better. It's the same. If you define this as W1, W0, and this is W1, so this will be better. This is true. If this is W1 and this distribution is W0, this is alpha. Okay, sorry about it. Okay.
And the other
This,
partition is
this, and this is beta. If we have the distribution this, so this is beta. Okay. The area under the curve of P of x given W1 between minus infinity to our decision boundary. So, is it clear? Okay. So, now let's do... so let's... so we have, let's find some properties of the RC curve. So, first of all, let's see that it is well defined. That means that if alpha of lambda 1 is equal to alpha of lambda 2 for some two threshold. Yeah. So if alpha of lambda 1 is equal to alpha of lambda 2, then beta of lambda 1 is equal to beta of lambda 2. Okay? How can you prove it? So we can apply the lemma Persson, the lemma of Neyman and Persson. And basically, if we have lambda 1 and lambda 2, two threshold tests that alpha of lambda 1 is equal to alpha of lambda 2, right? So we can apply the lemma first to alpha 1 and then to alpha 2, theta 1 and theta 2. So if we will apply to the first to theta 1, so alpha of theta 1 is equal to alpha of theta 2, this will bring us that beta of theta 2 is bigger than beta of theta 1, right? This is one direction, and just a second, I will apply it twice. Yeah, and we can switch between alpha, beta, theta 1 and theta 2, and we will get that beta of theta 1 is greater or equal to beta of theta 2.
Is it possible that theta 1 will be different than theta 2 if their alphas are equal? It's hard to fluctuate.
Is it possible that theta will be?
Yeah, it will be two different thresholds if alpha and beta are equal.
It can be, but it doesn't have, no. In general, it can be only if you don't have a ratio test. Then you can define some theta that it's not a ratio between them. It's something else, and then it will be possible. But in this case, no. Okay. Okay, and so this is, yeah.
According to the lemma, if alpha 1 is smaller than alpha,
It's not smaller or equal.
It's here. It's not.
but smaller.
Yeah, right.
But you wrote equal.
So yeah, but it's also
Because it's smaller.
it's smaller or equal.
But according to the lemma, it's smaller than smaller
Yeah,
or equal.
maybe we defined it wrongly at the beginning, but
What?
No, it's equal because it's output.
In the lemma, it's equal. It's smaller or equal.
Yeah. So equal is if they are equal, then it's smaller than equal, right?
It's smaller or equal in the lemma.
it's not written here, but that's why we try to understand if it's a mistake. We try
What?
to understand the problem.
No, the lemma.
If you define this way in the lemma, then it's fine.
It's defined in this way in the lemma. I didn't write it correctly.
No, you had, you had two parts. One with less or equal.
There are two parts. One that is less or equal, and one that is strictly less. Okay. Okay, and we can also prove. Don't have time. So, but basically, we can also prove that the RC curve is monotonically increasing in alpha. Okay. By the same trick that we did before. That's it. Questions? No. Okay. Great. כן. את הלמה?
את החוסר סימטריה. הבנתי למה הבנתי.
למה זה חוסר סימטריה?
מה ההבדל בין גרירה לאינטראקטיבית?
כי, אוקיי, אז החוסר סימטריה זה בגלל ש... yeah, so we are talking about the non-symmetric, why the lemma is non-symmetric. Okay? So basically, I can show you there is the proof of the lemma, but in the lemma, no, I will not show you like this. Basically, you have some test. Okay? You have some test lambda. Okay? And now you tell me that beta of lambda is greater than beta of lambda theta. Okay? Or greater or equal. Okay? No, I don't know anything about it. It can be any test.
Yeah, the more powerful test.
Yeah. It's more powerful in beta. What? Yeah, it's less powerful. Yeah, exactly. And so so now you don't, because you don't know anything about this test. It can be, I don't know. For example, choose one for anything. Every example that you see, choose one. Okay? So probably that it will have a bigger beta, right? For sure. But I don't know anything about its alpha. Probably it will be also a bigger alpha. Probably that in this case, if you choose one for everything, that alpha of lambda will be bigger than alpha of lambda theta, right? So this is not, so we don't have symmetry. So this will bring us that not alpha of lambda is smaller than alpha of lambda theta.
So why you say that we don't have any limitations like on alpha, because it's always a kind of system.
No, what? You didn't get
Like, I didn't
this?
get this far. You said
It seems to be the same. If I have S,
No, but you have,
I choose 0.
right?
For everything I choose 0.
Yeah. So you will have terrible alpha and terrible beta, right?
Yeah, but it seems to be symmetric. Because if I move my threshold, then I lose alpha and I gain beta, or gain beta and lose alpha. So to me, it seems like there is symmetry.
Just saying. When you say symmetric, what exactly are you?
That I can switch the words of alpha and beta, and I have the same.
that's symmetric, like better.
No,
I meant that I can switch the words of alpha and beta, and the lemma has to stay the same.
the role in what?
Because you have like.
Oh no, of course. Just a second. No. I thought that you mean something else. I thought that you mean that the lemma tells us, right? The lemma tells us that alpha of some lambda, when alpha of some lambda is smaller or equal to alpha of lambda theta, this will bring us that beta of lambda theta, lambda is bigger than beta of lambda. Okay? Of course that you can switch between alpha and between alpha and beta. Of course that it doesn't matter in this case. Yeah, of course. This is, of course, you can just switch between as the same as you can switch between the distribution. This is okay. No, this is okay. So you can.
I call alpha beta and beta alpha.
You just switch the distribution.
So I can do the same multiplication with the multiplication of both sides?
What?
To begin on the value, to check that it's possible to accept for this?
No.
That's the whole
Just a second. No, you can't. No, this is exactly the point. This is exactly the point. You can't. No, because you have it here. It's some test. You don't know anything about it. This will be true. That if beta of lambda is smaller than beta of lambda theta, then beta of alpha, then alpha of lambda is bigger or equal to alpha of lambda theta. This is true, but this is not true. Okay?
כאילו צריך להפוך גם את הסימנים.
Exactly.
So you mean for the equal sign that
Opposite sides work. Doesn't work for the same.
You have to switch the signs.
Yeah.
Think about it as this, like if this is A, B, so also 1, 2 is equal to
Not A,
not B,
not B.
not A.
Exactly. This is logic. You're right. This is a good way to prove it. This is logic. A that brings B. Yeah. Yeah, right. This is maybe. Did you learn logic?
Yeah, I know this
So
one.
exactly, this is logic. Again, it's nice way to prove it. Yeah. To say it.
לא, אבל אם אתה היית רוצה להכריז על ככה, זה היה באמת כאילו אחד הבנים שבא. בטח מתכוון לפגוע, כאילו, אז כאילו, בתוך זה.
והארו סטיקר,
כן.
מוגדרת פר מבחן, זאת אומרת, מבחנים שם יהיה לי הארו סטיקר שלהם.
היא מוגדרת פר... לא, יכול להיות לך, לא, מבחן, מה זאת אומרת? לא, יכול להיות לך המון מבחנים, כאילו כל, שאלה מה את קוראת מבחן, אם את קוראת מבחן כפונקציה של תטא,
נגיד אני הולכת...
איזשהו מבחן.
אין מבחן, אני כל הזמן עובדת אחד.
סבבה, אז איזשהו...
הארו סטיקר מכוער, אבל כאילו...
לא, מה זאת אומרת, אם את כל הזמן אומרת אחד, לא יהיה לך הארו סטיקר מכוער, יהיה לך נקודה במרחב הזה. זה לא קו, זה נקודה.
אם אתה יכול לדבר על הארו סטיקר, גם בהקשר של דברים שהם לא פשוט.
כן, בוודאי, אבל את מדברת עליהם במונחים של אופטימליות. ארו סטיקר זה במונחים של אופטימליות, אוקיי? במקרה threshold מביא לך אופטימליות. אבל אני יכול להגיד, אני זורק איזשהו מבחן, תזרקי מבחן, תקבלי נקודה פה. תזרקי מבחן, תקבלי נקודה פה. עכשיו, המבחן הזה יכול להיות פונקציה של תטא נגיד, או יכול להיות פונקציה של מה שאת רוצה, כן? ואז יש לך איזשהו קו פה, כן? עכשיו, את יכולה להגדיר את הקו הזה גם בעזרת סדרת מבחנים. כאילו, נגיד את אומרת, בואי נעשה...
כאילו, מה שתכונתי לשאול זה, האם הקו הזה תמיד מייצג את הבטא האופטימלית של אלפא?
כן.
או שהוא יכול לייצג גם את הבטא המבחן מסוים, שיכול להיות בטא פלוס או פחות?
את יכולה, אבל אז יהיה פחות מאופטימום. יכול להיות לך קו כזה, אבל יהיה לך פחות... כן, לא, רק האופטימלי.
רק האופטימלי, נקרא האופטימלי.
כן, זה עניין של זה, אבל בדרך כלל כן. אתה יודעת מה, תלוי במקרים, כשאנחנו מדברים בזה, אז הכוונה היא כזאת, כן. Yes.
Okay. So if that's how you prove it, so can you, I will do it as fast as possible. So this is correct, right?
Just a second. If lambda is smaller than that, yeah, this is correct.
Okay. Then according to this one. So yeah, this is correct, right?
Yeah, right.
But that's why.
But this is not correct.
So the only difference if you have an equal sign?
No. The only difference is, look, this and this is not the same as this. Even with the equal, without it, it doesn't matter. Because here, you see here and here you switch the signs.
But I can also do this. So like.
No, you cannot get this in this side. You will not get it by.
I'll try.
No, this is not true, but.
Like his friends don't know more than he doesn't like to do anything fun, so he makes up excuses for dating to God. Yeah, but he was lying because his friend knows more than he.
No, but
This is correct, right?
Just a second. if alpha of beta. No, this is not correct.
This is not correct.
This is not correct.
No, alpha is larger. Alpha of this is larger, then the beta is smaller. Why?
No, this is not correct because you don't know anything about this test. For example, I will choose this test will tell you to choose only one. All the time to choose one.
Wait a minute. But that's what you write here, right? This larger.
But you need, but if you change the sign, you also need to change the to change it's not. You change the sign, then you need to say not. And here you just change the sign. It was this, right? It was this and this, right?
No, just flip this.
Okay, you can flip it.
No, I just put the theta here and alpha here, right? And put the theta here, alpha.
But you cannot do it.
No.
You cannot do it.
Maybe.
Look. So let's start from the beginning.
No,
you have
change the notation of these two. So it's probably.
No, but the notation is important. This can be any test, and this is a specific ratio, likelihood ratio test. This is the ratio, the likelihood ratio test, or any ratio test in the general case. But it's not a general test that you can choose whatever you want. It's a specific. I telling you what is the test. Okay. And this lemma tells you that the test is optimal. Yeah. Likelihood ratio test.
But if I have exercises, I want to make them.
Okay. Maybe I missed that.
Yeah. Okay. Great.
I'm sorry to interrupt you again.
Yeah. Sure.
But I missed you. So could you explain this again?
What again?
This part. I couldn't follow.
Okay. So I'm trying to get the best some test. Yeah. That is optimal in the sense that I have some constraint on some alpha.
I want alpha smaller than this.
Yeah, this is my constraint, but I want that it will be optimal. That means that beta of my test will be minimal. Okay?
Under this constraint, I will minimize this thing.
Exactly. I want to minimize this thing with this constraint. Exactly.
Okay.
And the Neyman-Pearson lemma tells us that I only need to consider tests that they are the likelihood ratio test. Okay?
Okay.
Because it's optimal, because it tells me that the likelihood ratio test is optimal. So I only need to find theta or the decision boundary t in this case.
Okay.
So we found last week that alpha of likelihood ratio test in this case of the two Gaussians are the integral between t to infinity. This is alpha. This is definition of alpha. Okay, and this is equal to this. And we can find that the decision boundary t is equal to some function to the phi of 1 minus alpha prime. Okay? Okay?
So it's just reverse of this function.
Yeah, exactly.
Yeah, okay.
And we can find also beta. Okay? We can find beta. Now we don't have the constraint. I'm telling you to find the optimal test for these two Gaussians.
Okay, so now in this way you found the.
I found this is a number, right? This is alpha prime is a number.
Okay.
And so we get everything here.
So this is the alpha.
So this is the alpha and this is beta, right? And this will determine. This is define our seeker in the case of these two Gaussians. Okay?
Okay, cool. And
Good.
what's this part?
What?
What's this part?
This is if I want to find beta as a function of alpha. Right?
This is what?
Alpha.
Alpha given
Beta,
given alpha.
yeah, the function of alpha. I'm choosing alpha and I want to find the optimal beta.
Okay.
Okay, so of course, if I have the RC curve, if I'm choosing alpha, I know beta, right? I know 1 on my...
Where this formula come from? This is phi, right?
Yeah, this is this.
I
Right.
miscopied the
Yeah.
formula.
When he was like trying to understand everything on the Bible, where that's yeah, but I'm going to you.
Cool. Okay. Thank you.
No problem.
I think.
Okay.
אני לא כל כך מבין שהקטע הזה מספיק, אבל אני גם לא מכיר את הסוג הזה של ה...
פי זה בסך הכל פונקציה, שאתה יודע אותה.
פי מינוס 1, מה שאתה יודע שזה
איך אתה יודע שזה זה? כי זה גאוסיאן עם... זה גאוסיאן עם ממוצע אחד, ועל מנת לעשות את הסטנדרטיזציה צריך בסך הכל להוריד את הממוצע שלו. אם זה היה גאוסיאן עם ממוצע 0, זה היה פי של t.
פי של t,
תסתכל, אם זה היה גאוסיאן עם ממוצע 0, ווריאנס 1, אז הדבר הזה זה בדיוק פי של t. זה ה-CDF של גאוסיאן 0, מה שכתוב פה זה ה-CDF של גאוסיאן 0 ושל ממוצע 1, של ממוצע 0 ווריאנס 1. אוקיי? שזה בדיוק זה, אם זה היה כאן גאוסיאן ממוצע 0 ווריאנס 1. אבל כיוון שזה לא, הווריאנס הוא אומנם 1, אבל הממוצע הוא גם 1, אז אני צריך לתקנן אותו, לעשות סטנדרטיזציה. לכן זה בסך הכל אומר להוריד 1. אז זה לא פי של t, זה פי של t מינוס 1. אז אם השונות היא לא 1, אז צריך לחלק בשונות. כן, זה מה שראינו שבוע שעבר, שעל מנת שכל משתנה גאוסי אתה יכול להפוך אותו למשתנה סטנדרטי גאוסי. בבקשה.
Yeah, of course.
Okay, so now let's return to the RC curve to one final thing. If we have, what will happen if we will move the two distributions? Okay, now we don't want to move the threshold, we just move, we'll separate the two distributions. How it will influence the RC curve? It's what? Right. So if we have two distributions and now we will move them away from each other. So now, for example, we have this distribution and this distribution. So our RC curve will change from this is alpha, this is y minus beta. It will change from this to this one. Okay? So as we increase, this is this is the d prime. It also. Did you see it in some other course? D prime. Yeah. Okay. So so this is d prime. So if we will increase d prime, the distance between the two distributions, we will get a better separation, and we can get a better result or a better optimal test. Okay. Great. So now let's go to another other topic. Now we are interested in multiple observation. Tali started to talk with you about multiple observation, right? So now we have x1 to xn IID random variables. These are the observations from some distribution P of x given Wi. Okay? And just notice that they are independent only given the world state. Okay? They are not independent in general. Only given the world state, they are independent.
Can you explain what the difference is
Between
conditional independent?
just only after you know the world state, you can say that they are independent. Like the definition of it, of course, this is not true. Of course, that the P of x1, for example, if we take their, we cannot. Maybe the most important thing that we cannot decompose P of x1 to xn to their product. Okay, we cannot do it in general because they are not independent. We cannot do. Okay. But because they are independent, given the world state, we can factorize the likelihood ratio test. So we know that the likelihood ratio test is P of x1 given 2xn given W0 divided by P of x1 to xn given W1. Okay? This is the likelihood ratio test for multiple observations. And now, how can we decompose it?
X1 given omega?
Exactly. It's the multiplication of P of xi given omega 0 divided by P of xi given omega 1. Yeah. Multiplication on I. Okay?
The prior.
In?
The ratio of the prior.
No, this is the
Oh, yeah.
okay? Now let's suppose that theta is equal to 1. Yeah. Just for a simplest. So this we want to compare to 1. And now we can take the log of both sides, and we'll get that the log likelihood ratio test of our observations is equal to 1 over n, 1 divided by n, sum of I goes from 1 to n, log of the ratios. P of xi given omega 0 divided by P of xi given omega 1. Okay? And this is not smaller than 0. Okay, I just took the log of this term. Because we have here a multiplication of n.
But it's not to the power of n.
To the right. No, you are. No, you are. This is okay. Sorry, yeah. So this is the log likelihood ratio test, but most of the time we want to look on 1 over n, the log likelihood ratio test, and then we will get that it's equal to 1 over n. Okay? Okay. So now, yeah, question? What? I will. This is we take a theta that is equal to 1, and log of 1 is 0. Okay. So now we want to find the errors. Okay. So so now we want to find the errors, alpha and betas. So how can we do it? So we'll define a new random variable, zi, that is equal to log of p of xi given omega 0, divided by p of xi given omega 1. Okay? And now we can look on the likelihood ratio test as sum over zi. Okay? Now we want to check what is this zi when n goes to infinity. Okay, in the limit that n goes to infinity, we want to check what is the distribution of the likelihood. So what we know about sum of a lot of things, sum of a lot of what? The central limit here, right? So we know that it converges to the normal distribution with some mean and some variance, and we know that the mean and the variance depend on the mean and the variance of zi. Okay, so let's find it. So let's assume that the variance of z given omega I is equal to some sigma I to the square. Okay? What? Yeah. And now we want to look on the expectation of this. Okay, we want to look at the expectation of the likelihood, or we want to look at the expectation of z given w. Okay, what is the expectation of z given w? So the expectation of z given w is equal okay, so the expectation of z given w, given omega is equal to what? Sum over. Okay, so we need to separate what? No, it's z. It's the sum. What?
No, z given w, right?
Z given, yeah, it's z given w. So yeah, it's z given omega. So we need to separate the two cases when omega is equal, when the real world state is omega 1, or when the real world state is omega 0. Okay? So when the real world state is omega 0, we will get what we will get. So this is equal to sum, right? Sum over all of our observations. P of x given omega 0 log of p x given omega 0 divided by p of x given omega 1. Okay? Is it clear? And this is equal to, what is this term? You saw it in class.
The DKL, right?
Right, between?
P x omega 0 and px given omega 1.
Right, exactly. So this is exactly the DKL between P of x given omega 0 and P of x given omega 1. Okay? And in the case that omega is equal to omega 1, what is this term?
You get minus DKL,
Right, minus the inverse. So let's see. So this is equal to P of x given omega 1 log of P. What? So what is this term when omega is equal to omega 1? Okay? So so we need to sum over x given omega 1 instead of x given omega 0. Okay? So it's a log of x given omega 0, right? P of x given omega 1, and this is equal to minus the DKL of P of x given omega 1 and P of x given omega 0. Okay? So at the end, we got that in the case that omega is equal to omega 1, it's the DKL between P of x given omega 0 and P of x given omega 1. And in the case that omega is equal to omega. And in the case that omega is equal to omega 1, this is minus the DKL between P of y given, P of x given omega 1 and P of x given omega 0. Okay? And so and the variance goes as if so the variance of the likelihood xn given omega goes as sigma to the square 0. In the case that omega equal to omega 0, it goes as sigma 0 to the square divided by n. And in the case that omega is equal to omega 1, it goes as sigma 1 to the square divided by n. Okay? As we saw last week. So now, what we have? So what we got here? We got that in the case that our true probability is omega 0, the likelihood ratio test will go as the normal distribution, which means that is equal to the DKL between x given omega 0 and x given omega 1, with variance that goes as sigma 0 to the square divided by n. So as we will have more and more examples, the variance distribution will be concentrated around the mean, and the variance will decrease. Okay? And in the case that we will have the true probability, the true distribution is omega 1, the mean will go as the DKL minus the DKL of x given w omega 1 and x given omega 0. Okay, so we will get, just a second, as we will see more and more examples, we can separate between these two distributions in a better way. Yes?
Isn't the variance supposed to be n over n squared?
No.
The variable is 1 over n over z, and the variance.
No, but if you take the likelihood, at the end only we need to divide it by n. Maybe I will check. Okay. Questions? Yeah.
Did we see that we get less eval probability by the terms of convergence?
What do you mean?
If you get the two distributions parallel,
Yeah.
then we should see it also with the eval probability.
Alpha and beta, do you mean? Yeah, sure. So I said, basically, if we know that if we have, so the distribution of the likelihood.
Isn't that what we try to do with Z?
Exactly. Yeah. Yes. So we can see that the likelihood, right? That we have two distribution. If the likelihood distribution, if we the true distribution is omega 0, and if the true distribution is omega 1, okay? So if this is D1 and this is D0, okay? So the mean, so we know that as n goes to infinity, this will be as a normal distribution, and this is the mean, is the DKL, this DKL, and this mean is this DKL. Okay, and they will getting narrower when we will get more and more examples. Okay, questions? Okay, so just the main point of all this this path is just to emphasize that as we will get more and more examples and more observations, we'll be more and more accurate in our decision. Okay? So this is exactly it's the same as you can look on, as Tali said in the lecture, you can look on to if it's a sequential decision, then you can define your two thresholds, and as you will go to as n will become bigger and you will see more examples, then eventually you will be above the threshold, okay, or below it if it's the minus. Okay, great. So let's talk about DKL, the KL divergence. So the definition of the KL divergence, it's a very important it's a very important distance that we will use it a lot, especially in information. So the definition of it, the DKL between some distribution P and Q is equal to sum over X, P of X log P of X, Q of X, okay? And this is also the expected value according to P of log of P of X given divided by Q of X, okay? So, or in the continuous case, we have integral. So, this is the definition. And now, let's see some properties of this. So, some properties. So the first property is that the DKL is non-negative. I think Tali proved it here, right? So
When you write flow, which base? The natural or 10?
So it depends. It can be both, and the definition holds for both of the log.
The proof that Tali showed us was based on the LAN.
Okay. Yeah, in the course we will use LAN. This is the base that we will use in the course. So first of all, it's non-negative. So the DKL between P and Q is not smaller than 0. The second thing, did you see? Can you see it here? No. Yeah.
I can, but I think most of them.
Okay. So. Okay, so the DKL between P and Q is equal to 0 if and only if P of X is equal to Q of X almost everywhere, in every X in the domain of both of them. Okay? And it's very simple to prove it. So let's prove it. So the minus the DKL P of X and Q of X is equal to the sum over X P of x log P of x Q of x, and we can use the inequality that log of x is not bigger than x minus 1. Okay? We can use this inequality, and we will get that this is not bigger than P of x 1 minus Q of x divided by P of x. Okay? And this is 0, because we have here sum over P of x and sum over Q of x, so this is 1 minus 1, and we will get here 0. Okay? And another property of the DKL that it's not symmetric. Okay, so the DKL of P and Q in general is not equal to the DKL between Q and P. This is the here. This you don't know why this is equal to 0.
No, I know it's equal to 0, but
so minus the DKL.
DKL is smaller than 0.
Exactly. So the DKL is bigger. Is not. Is larger. Yeah.
Like the first property is
It's a positive. Okay. And it's not symmetric. Okay. Great. So.
Can you say something more about the DKA, like what does it represent? Not the math, like what does it mean in what we're doing? Intuition maybe?
So the intuition is a distance between two distributions. You have some distribution and you have other distribution, and you want somehow to define their distance, how much one distribution is close to another distribution. Okay, so there are many ways to define distance between distributions. So this is one of them. And let's see, let's see what does it mean in the Gaussian case. Okay, so we have time. Yeah, let's do it. So yeah. So we have two Gaussian distributions, and we want to know what is the DKL between them. Okay, so F0 is distributed as Gaussian with some mean and variance, and F1 is also Gaussian with some mean and some variance. And we are asking what is the distribution, what is DKL between these two distributions. Okay? So, what we need to do? Substitute in the definition, right? So, it's the integral between minus infinity to infinity f0x log f0x divided by f1x dx. So this is the definition. Now,
Why do you decide to do it F0 and F1 and not F1?
because f0 is the first one here.
No, I mean, what you want to find a DKL.
Right. I can try to find. I can find also the decay between f1 to f0. But now I want to find. No. It's just names. Okay. So this is equal to the integral between minus infinity to infinity of f0 log of sigma 1 divided by sigma 0. The exponent of, let's write it here. So it's the exponent of minus x minus mu 0 to the square divided by 2 sigma 0 to the square plus x minus mu 1 to the square divided by 2 sigma 1 to the square dx. Okay? I just put the two Gaussian, the distribution of them. Now the log and the exponent are cancelled each other, and we will get that it's minus the integral between minus infinity to infinity f0 of x log of the ratio between sigma between sigma 1 and sigma 0 minus x minus mu 0 to the square divided by 2 sigma 0 to the square plus x minus mu 1 to the square divided by 2 sigma 1 to the square dx. Okay? Now let's open it. Let's open this. Maybe. And we'll get that this is equal to log of the ratio between sigma 1 and sigma 0 minus the integral between minus infinity to infinity f0 x minus mu 0 to the square divided by 2 sigma 0 to the square dx plus 1 over 2 sigma 1 to the square integral f0 x minus u1 to the square dx. Okay, I just opened the bracket. So if this is B and this is A, this is B and this is A, so A is equal to minus infinity, the integral between minus infinity to infinity f0 x minus mu 0 to the square divided by 2 sigma 0 to the square dx. And what is this? So let's see it maybe more. If we take outside 2 sigma 0 to the square, the integral between minus infinity to infinity f0 x minus mu 0 to the square dx. What is this term? It's the variance, right? So this is the variance of f0. So we'll get that all of this is equal to half. Okay?
Why is it the variance?
This is the definition of the variance. Because mu 0 is the mean of f0. This is exactly the definition of the variance. You can count later, but this is exactly the definition that we saw last week. One of the definitions. And now b is equal to the integral between minus infinity to infinity f0 x minus mu 1 to the square dx. And now we can do some trick. We will add and substitute. We will add we will add mu 0 to this term. We will add and subtract mu 0, and we will get that it's the integral between minus infinity to infinity f0 x minus mu 0 plus mu 0 minus mu 1 to the square dx. And you can open this and you will get that this is equal to the integral between minus infinity to infinity of f0 x minus mu 0 to the square dx plus 2 mu 0 minus mu 1 times the integral between minus infinity to infinity f0 x minus mu 0 dx plus let's write yeah, sorry. So let's write it here. It's also in my notes, so you can take it from there. So plus the final term is mu 0 minus mu 1 to the square times the integral between minus infinity to infinity f0 x dx. Okay, so now let's see. Okay, so what is this term? What? So what? Sorry, this term. What is this term? Sigma 0, right, to the square, right? What is? What? What? This term. Yeah, exactly. This is 0. And now this term. What is this term? This is 1. Exactly. And so if we will putting it all together, we will get that the DKL between f0 and f1 is equal to log of sigma 1 divided by sigma 0 minus half